Okay, so let's go ahead and take a look at this section. This section, we're going to do calculus stuff related to parametric equations. So remember what we did in the previous lesson where we eliminated the parameter, so we got rid of the value of t. So we can do derivatives with parametric equations. And so the definition of the derivative with a parametric equation, so if I have my dy dx, is taking the derivative of y, so my dy dt, divided by dx dt. So if I wanted to find the value of dy dx, if I have these two parametric equations, I'm just going to write the equation for dy dx. So I first need to find dx dt. So dx dt is equal to 2t plus 3. And then dy dt is equal to 4. And then all I'm going to do is I'm going to take the ratio of the two. So my dy dx is equal to 4 divided by 2t plus 3. And that is my derivative. Now I can do derivative at a point too. So this little definition here, I can plug in any value in I want for t. So like example 2, if I want to write the equation of the tangent line at this particular point, then what I'm going to do is I'm going to first find the slope of the tangent line, which means I need to find dy dx at pi over 6. So first dx dt is equal to negative 4 sine t, and dy dt is equal to 5 cosine t. So then dy dx is equal to 5 cosine of t divided by negative 4 sine t. And then I'm going to evaluate this at pi over 6. So dy dx at theta is equal to pi over 6 means 5 cosine of pi over 6 divided by negative 4 sine of pi over 6. Cosine of pi over 6 is root 3 over 2. And sine of pi over 6 is 1/2. So then I get 5 root 3 over 2 divided by negative 2, which is 5 root 3 divided by 2 times negative 1/2. So I get 5 root 3 divided by 4. So that's the slope of my tangent line. Now I need to figure out my x and my y coordinates. So I know that x is equal to 4 cosine of t. So x is equal to 4 cosine of pi over 6. And the cosine of pi over 6 is root 3 over 2. So this is, not 2, 4 times root 3 over 2. And then I get 2 root 3. And then y is equal to, not 4, 5 sine of t. So that means that y is equal to 5 sine of pi over 6. And sine of pi over 6 is 1/2. So I get 5 halves. So then my point slope form is y minus 5 halves is equal to 5 root 3 over 4 times x minus 2 root 3. And you can go ahead and leave it in point slope form, unless you're on a multiple choice test where you have to pick out which one is your equation or tangent line. Okay, so example 3, I have this curve, it crosses at the origin, write the equation of the tangent lines to the curve at the origin. So again, dx dt, so if I need to find dy dx, so dx dt is cosine of t, dy dt is equal to 2 cosine of 2t. So then together, dy dx is dy dt, which is 2 cosine of 2t divided by cosine of t. And now, I want to go ahead and write the equation of the tangent line. So dy dx evaluated at the origin, 0, 0, is equal to 2 cosine of 2 times 0 divided by cosine of 0. Cosine of 0 is 1. Cosine of 2 times 0, same thing as the cosine of 0, which is 1. So all of this becomes 2. So then I'm at the origin. So then y minus 0 is equal to 2 times x minus 0. So y is equal to 2x. Okay? So then, more Same thing. So take a moment, see if you can figure out what the slope of this curve is. Now notice something, because you probably have already started. Notice something, and that is my x and my y both are products. So I'm going to need to use product rule when I take the derivative. So dx dt is equal to cosine of t negative 2 e to the negative 2t plus e to the negative 2t negative sine of t, and then I can simplify this. So negative 2 e to the negative 2t cosine of t minus e to the negative 2t sine of t. And then I can do my dy dt. So same thing, product rule with dy dt. So sine of 2t negative e to the negative t plus e to the negative t 2 sine of 2t. So then negative e to the negative t sine of 2t plus 2 e to the negative t sine of 2t. And now what I'm going to want to do is I'm going to want to write this as dy dx. So I need to take my dy dt, need to take my dx dt, and I need to divide them. And then I'm going to plug in 0. So dy dx is equal to negative e to the negative t sine of 2t plus 2 e to the negative t sine of 2t divided by negative 2 e to the negative 2t cosine of t minus e to the negative 2t sine of t. So I have this, and now I'm going to plug in 0. If you wanted to plug in 0, because we're going to solve for dy dx, if you wanted to plug in 0 in for dy dt and dx dt separately and then take the ratio of them, that's totally fine. Dy dx, but I'm good with making myself live through some torture. So I wrote the ratio first. So negative, plug in 0, sine of 2 times 0, plus 2 e to the negative, plug in 0, sine, and there is no negative 0, but I'm just leaving all the signs there. 0 divided by negative 2 e to the negative 2 times 0, cosine of 0, not plus, minus e to the negative 2 times 0, sine of 0. Well, sine of 0 is 0. And the cosine of 0 is 1. So in the denominator, I get something that's not 0. But in the numerator, all of them are being multiplied by the sine of 0. So this will give me 0. Okay? So the slope of my tangent line, or the slope of the curve, is equal to 0. Now I want to do example 5. And this is a little bit longer of a video lesson, so bear with me. So example 5, and we're going all the way to example 9. But we have example 5, so we're halfway through, almost. I want to write the equation of the tangent lines of these two when they're horizontal and vertical. So again, dx dt, so 4t, dy dt, (3t squared minus 2). And if I wanted to find dy dx, I would take the ratio of the two. But we know, and I can write dy dx for you, so just so you guys get practice, 3t squared minus 2 over 4t. So dy dx is horizontal when dy dx is equal to 0. So that means that my numerator is equal to 0. So that's 3t squared minus 2 is equal to 0. So that means 3t squared is equal to 2, t squared is equal to 2/3, t is equal to plus or minus root of 2/3. Which if you want to rationalize the denominator, you're more than welcome to, or you can leave it this way. So that's when dy dx is horizontal. When dy dx is vertical is when dy dx is undefined. and dy dx is undefined when my denominator is equal to 0. So 4t is equal to 0. So t is equal to 0. And that's when I figure out when dy dx is horizontal and vertical. Same idea with equations of tangent lines. Back when we did implicit differentiation, and we were like, oh, when's it horizontal? When dy dx's numerator is equal to 0. When's it vertical? When the denominator is equal to 0. Same idea. So we haven't really changed a whole lot. So example 6, I want to figure out when I have a maximum value, or what time it is when I reach my maximum value. So I want to figure out my maximum value. So I need to take the derivative. So dx dt is equal to 50. dy dt is equal to 40 minus 20t. So dy dx is 40 minus 20t divided by 50. And I'm going to set this equal to 0 because I need to figure out my critical numbers. So everything works just kind of the same way that we did back in the fall semester, but now we're just doing it with t being the independent variable. So I multiply both sides by 50, so I get 40 minus 20t is equal to 0. So 20t is equal to 40, so t is equal to 2. And I want to figure out max and min, so of course, I'm going to do the chart. So interval, test value, sign of dy dx, and conclusion. So I'm going to go negative infinity to 2, 2 to infinity. I'm picking t equals 1 and t equals 3. And now when I plug it in, into dy dx. Here's my dy dx. When I plug in 1, I get something bigger than 0. So dy dx is bigger than 0. And when I do this into my 3, into my derivative, I get less than 0 when I plug in 3. So this is increasing. This is decreasing. So because it goes from increasing to decreasing, we know that there's a maximum value there. So now the question is what are the x-coordinates for this maximum value? So I know what t is equal to 2, so I want to find x of 2, which is 50 times 2, which is 100. And then I want to find y of 2. So that's 40 times 2 minus 10 times 2 squared. So 80 minus 40, which is 40. So my coordinate point, or my value for x and y, is 140. Okay. So now we need to look at second derivative with parametric equations. And second derivative with parametric equations just means that we need to look for concavity. So we're going to do this just mainly so that we could figure out concavity of the function. Okay, so let's take a look. And I proved like why this works here. So y d squared y over dx squared is equal to this. Now what it is, what d squared y over dx squared is equal to, what it is in parametric equations and in vectors. So you'll see that in vectors as well. You're going to take your dy dx. So you'll first find dx dt, then you'll find dy dt. Then you need to find dy dx. Then you need to take the derivative of dy dx and divide it by dx dt. So that makes it a little bit different than what we did with second derivatives in the fall semester. Okay, let's look at an example of finding the second derivative and the concavity. So I first need to find step 1, dx dt and dy dt. So dx dt is cosine of t, dy dt is equal to negative 2 cosine of 2t. So dy dx is equal to negative 2 cosine of 2t divided by cosine of t. And now I need to take the derivative of this. So the notation I'm just going to use is d dt of dy dx. What that means is I'm just taking this notation here, just means I'm taking the derivative of whatever is inside this parentheses here with respect to time. So this requires quotient rule, and I may run out of room, so let's write a little bit smaller here. So cosine t negative 4 sine of 2t minus negative 2 cosine 2t times negative sine of t, all divided by cosine of t, the quantity squared. And then I'll clean it up just slightly. So negative 4 cosine t sine of 2t minus 2 sine of t cosine of 2t, all divided by cosine squared of t. And then that is my numerator of my d squared y over dx squared. So I'm plugging in negative 4 cosine of t sine of 2t minus 2 sine of t cosine of 2t divided by cosine squared of t. All of this is being divided by cosine of t, which is my dx dt here. So first step was to find that. Second step is to take the derivative of dy dx. Third step is now to write this like this. Now, I want to go ahead and I want to plug in, I want to know the concavity of the function at t is equal to pi over 6. So what I need to do is I need to find d squared y over dx squared at pi over 6. Now, this cosine of t in the bottom and that cosine squared of t in the top, when you invert and multiply, it's going to give you cosine cubed of t. So I'm going to skip that kind of step right now. So you're going to get negative 4, maybe I shouldn't skip the step. So this is negative 4 cosine of t sine of 2t minus 2 sine of t cosine of 2t divided by, because you're going to invert and multiply this is going to become cosine cubed of t. Okay. So negative 4, I'm going to plug in pi over 6, so cosine of pi over 6, sine of 2 times pi over 6, minus 2 sine pi over 6, cosine 2 times pi over 6, divided by cosine of pi over 6, the quantity cubed. So then I plug in everything, negative 4 root 3 over 2. That's also root 3 over 2. Minus 2 times 1/2 times 1/2, all divided by root 3 over 2 squared. And then when you simplify this, you're going to get negative 12 over 2 minus 1/2 divided by 3 root 3 over, oh, this should be cubed, over 8. So you get negative 13 over 2 times 8 over 3 root 3. Is this positive or negative? It is less than 0. So since d squared y over dx squared at t is equal to pi over 6 is less than 0, then the function is concave down. Okay? Maybe I went too fast. Okay, there you go. So now, let's determine the concavity at 3. Same process that we just did. So I'm going to find dx dt. So 4t. I'm going to find dy dt. So 3t squared minus 2. I'm going to then find dy dx. So 3t squared minus 2 over 4t. I'm then going to find d dt of dy dx. So that's quotient rule, 4t, 6t, minus 3t squared minus 2 times 4, all divided by 4t, the quantity squared. So I get 24t squared minus 12t squared plus 8, all over 16t squared. So I can simplify that more. 12t squared plus 8 over 16t squared. Everybody's divisible by 4. So that makes 3t squared plus 2 over 4t squared. Okay. And now I'm going to go d squared y over dx squared. So I get 3t squared plus 2 over 4t squared. That's what I just found. And then divided by my dx dt, which is 4t. So then I get 3t squared plus 2 over 4t squared times 1 over 4t. So I get, because I inverted multiply my denominator, so I get 3t squared plus 2 over 16t cubed. I want to figure out, is this bigger than 0 or less than 0 when I plug in 3. So I get 3 times 3 squared plus 2 over 16 times 3 cubed. Again, bigger than 0 or less than 0, this is going to be bigger than 0. So since d squared y over dx squared is bigger than 0 at t is equal to 3, then the function is concave up. Okay. So now we're going to do one more thing, which is finding arc length. So arc length is like circumference. So it's the distance around that the particle would travel. Okay. So let's take a look at finding the circumference of the circle that's defined by x is equal to a cosine of t and y is equal to a sine of t. So I'm going to use this formula. What this formula says that the arc length, or the length of the curve, is equal to the integral of the square root of dx dt squared plus dy dt squared. So dx dt is equal to negative a sine of t. dy of t is equal to a cosine of t. So now my arc length, and I'm going all the way around the circle, so that's what? 0 to 360 degrees, or 0 to 2 pi. We are going to only use radians. Square root negative a sine of t squared plus a cosine of t, the quantity squared, dt. So I get L is equal to the antiderivative from 0 to 2, square root a squared sine squared of t plus a squared cosine squared of t dt. So L is equal to the antiderivative from 0 to 2. There's a common a squared in there, and I'm left with sine squared t plus cosine squared of t dt, which is sine squared plus cosine squared is 1. So 0 to 2 of a squared dt. Sorry, 0 to 2 pi. So now square root of a squared is just a, so this is the antiderivative from 0 to 2 of a dt. 0 to 2 pi. I keep doing that, I'm sorry. So take the antiderivative of a with respect to t. So this is a of t evaluated from 0 to 2 pi. So that's 2 pi a minus 0 times a. So I get 2 pi a. 2 pi a is the same thing as 2 pi r with finding the circumference of a circle. And those two relate to each other. Okay, so let's take a look at example 10. And I wanted to have it kind of written out for you guys already because I didn't want it to be too messy for you, where you wouldn't be able to figure out what we were doing. So let's take a look at let's go ahead and take a look at your arc length. So first step, again, I take my x of t, and I'm going to find dx dt. And then I'm going to find dy dt. And I have to use product rule. So again, second times the derivative of the first times the derivative of the second for my x. And then my dy dt, second times the derivative of the first plus the first times the derivative of the second. And I did go ahead and I simplified it a little bit. And then I'm going to plug it in to my formula here. So I plugged in my dx dt. I plugged in my dy dt. Now, in order for you to calculate this arc length from 0 to 5, you're going to have to use your graphing calculator. So let's be clear about what I did. So what I did, I'm going to change colors here. What I did is I plugged this guy into y1. He's the same as this guy here. Then I plugged in this guy in, I'm sorry, he's not the same as that guy. He's the same as this guy. And then I plugged this, the sine one, into y2, which is the same as the second one. So this is my y2, and this is my y1. So then what I was able to do in my calculator is go y1 minus y2 squared plus y2 plus y1 squared, and then everybody square rooted when I did my fnit with my graphing calculator. And when you do that, you should get 755.885. And if you don't, please let me know. Again, I did another one with sine and cosine. So again, you find your, change colors here, find your dx dt, find your dy dt, and plug them in. Okay, when I plugged them in, again, I would have plugged in, you know, like a y1 and then squared it, and a y2 and then squared it, and used bars. When you do that, you should get 28.362. Okay, and so that finishes our parametric equations with calculus section.